Okay, now what we are looking at is a solution for manipulators which are stiffer, right. So, when you have serial chain manipulators, right. So, in which you have when you have a sequence of links going from the base to the top, then the outboard motors are carried by the inboard motors. So, there is increasing mass, and then you cannot actually lock a motor in a particular position. So, if you remember a little bit of your controls, the way motors lock a link or a joint angle into a particular position is because you give a command signal, say go to theta is equal to 30 degrees, and then if you deviate from 30 degrees you get error signal and a torque is produced which is proportional to it or based on proportionality or integral or a derivative of the deviation. So, there is always an effective stiffness of a joint, okay, and that depends on a combination of roughly the proportional control rate, right. And you cannot make the joint infinitely stiff, because if you increase the proportionality constant too much, then what happens? It becomes unstable. So, there is a limit to which you can push it. So, each joint has a compliance which is a mix of the capability of the motor and the controller that you have designed. So, when you are cascading such stiffnesses in series, then what happens to the net effective stiffness? Then 1 upon k is equal to 1 upon k1 plus 1 upon k2 multiplied by momentum, so on and so forth. But in general, the stiffness which you have at the end effector will be much less than the stiffness of each individual actuator. Now, what we are looking for a solution is in which we have multiple connections to the base. From the end effector we have multiple connections to the base. Now, when you have stiffnesses in parallel, then the stiffnesses add. So, your net end effector stiffness will become much more than the stiffness of individual actuators. So, that is the whole idea. So, if you want a stiff system which can take loads and not deviate too much, then that is the preferred option. Okay. So, now if all the actuators are connected to the end effector and the base, then the system is called a parallel chain manipulator. It is a pure parallel chain manipulator. If there are multiple connections to the base and the end effector, but all of them are not connected to both, system is called a hybrid chain. Okay. So, if you look at typically you look at the human body, think about it, you have legs, right, both of them are connected to the ground, they are connected to a pelvis, right, but your leg you could roughly say is two links, right, joined together at the knee. So, there is a serial chain and there are two serial chain connected in parallel. So, these kind of things are called hybrid systems. Okay. So, you can start by looking at planar systems. So, this is an example. So, this is not a pure planar robot, as you can see, because there are these two links which are there. So, this is essentially a hybrid planar one. So, here is your end platform. So, as you move these motors, you will end up moving this. So, essentially the platform can move in x, y and also rotate. You can control all the three motions together. Okay. So, this you can make quite easily, it is not very difficult to make and manipulate. You just have to make it stiff enough so that the joints have very small play, okay, because if the joints have play, then you are losing out on the stiffness aspect of it. It is a construction difficulty, but otherwise it is fine. You can see this is simply made. So, this is a more general thing which is a hexapod, which is a spatial mechanism with 6 degrees of freedom. This you can see is not a real device, it is only a mock-up, okay, a CAD model of it. Now, what you have here is you have these actuators. Okay, so, these are linear actuators and they are connected. So, there are 6 of them which are connected to the base and also to the top, and they are connected typically by spherical joints so that they can move in, rotate in all directions, and then they expand. Okay, these are linear actuators. Now, if you have a spherical joint here and you have a spherical joint here, then along the line you can spin the actuator. Right? If you have any two spherical joints and you have something connecting it, you can spin it about that axis. But that does not change anything about the platform. So, that is effectively a redundant degree of freedom. And what really happens is, you are not going to have an actuator which really looks like this. You will see a real picture later. But you are going to have wires or hydraulic lines going into these actuators. So, if you allow that free spin, then as the platform is moving, that thing will move around and they interfere with each other. So, what is done is, typically you have a 2 degree of freedom joint here and a 3 degree of freedom joint here. So, that takes away that single degree of freedom which is there, which is the spin axis. So, then the system becomes more stable and predictable and is in control. Okay. So, now if you look at it, what is the number of links in the system? So, you definitely have the base, that is one link, then you have the platform which is 2 links, right, and then each leg consists of 2 links which move with respect to each other over the sliding joints. So, total of 14 links, right. What is the number of 3 degree of freedom joints? 6 of them, like I said, at the base. Number of 2 degree of freedom joints, 6 at the top, and number of 1 degree of freedom, which are essentially sliding joints, you have 6 of them, 1 in each leg. So, what is the total degree of freedom? So, it is 6 times 14 minus 1, 6 and minus 1 minus. So, for the 3 degree of freedom joints you subtract 3 degree of freedom per joint into 6 of them, then for 2 degree of freedom joints you subtract 4 degrees of freedom into 6 minus 5 into 6. So, you are left with 6 degrees of freedom. So, if you allow the links to slide about the joints, then the top platform can have 6 degrees of freedom. You are familiar with this formula, right? You should have done this in the kinematics course. Okay. And you also know there are several exceptions to this, right? This is a very general formula which, have you heard the statement, general statements are generally false? No? Never heard it? Really? Huh? Yeah. Who is this attributed to? Anyway, homework, huh? Find out. It's one of my favorite statements.
So statement will be like all generalizations are false, including this one.
No. It's a general statements are generally false. I mean, it's a colloquial statement. So, but it's attributed. So, it's homework. You can just wiki it. Okay, you'll find out. So, this formula, general formula, is there, but then there are so many exceptions to it. Okay. So, as long as all of these, so if you make this and this come to a same one point, then there will be a problem. If you join them both to the same point, there will be a problem. There are a couple of other situations where this will be a problem. If you attach all of them, if you spread all of them at 60 degree angle and you spread all of them at 60 degree angles on the top, even then you will have a problem. Okay. And all the link lengths are the same, then you will have a problem. So, there are lots of problems with this issue. So, just because this has 6 degrees of freedom does not make it a practical device. We have to ask other questions. The most important question is, if I lock all the sliding joints, what is the degree of freedom? It will become 0, right? Because if you lock all the sliding joints, then essentially these becomes fixed legs. So, the number of, or if you lock all of them, then the loss here will be more. it will become 6 into 6, so it will become 0. That means if I lock all the legs, then the top will not move. Okay. If I allow sliding about only one leg, then I will have only 1 degree of freedom. So all of these are important questions to ask when you devise a new system, because we want to know whether it is controllable, whether it is lockable. Okay. So if I just pick up I don't know. So if I just throw it up, this thing in space has 6 degrees of freedom, right? It does not make it a useful device. I need 6 controllable degrees of freedom. So please remember that. Okay. So quite trivial, but so when you analyze a system, you should ask these kind of questions, before you start working on it. Is it controllable? Can I lock it? Anyway. So you can have variations of this. So if you look at this one, so what you do is you create a universal joint here, right? So this cone-like thing can move about this point, okay, and so you can have actuators. So if you have 3 actuators, then the top will essentially rotate about this, and you can control the 3 rotary degrees of freedom. It's a reasonably simple concept. So you're pushing with 3. So this is very similar to the platform, the video which I showed you last time. So you can have 6, and here they are coming down to a single point. Okay. And then you can have delta manipulators. Now this is interesting. So there is a motor which has this axis, okay, and then you have this axis. So this axis is always parallel to the motor axis, right? And since this is a parallelogram mechanism, then this axis will always stay parallel to this, okay, which means there is this line on the top platform which stays parallel to, which stays essentially always horizontal, okay. So you have this line which is horizontal, you have this line which is always horizontal, and then the line connected to the third leg which is always horizontal. So if you have 3 lines in a plane which are always horizontal, that means the platform will always stay horizontal, okay. So it's a interesting concept, right, and it's again parallel in nature, so it has great stiffness, and then I showed you the phenomenal speed at which it works. Okay, so this is one concept. Yeah.
Sir, in that previous delta manipulator, can it move only in one direction?
No, it can move this, all 3. It just the top platform always stays parallel. It does not lose its attitude. If the joints are, all the joints are made properly and the joints don't have play. So theoretically you cannot have a absolutely rigid joint, but
Sir, if at a particular moment that end effector is symmetrically placed over the body at the center of the body, and then I try to move it towards one particular motor in that particular plane itself.
you move only one motor.
I move the end effector towards one motor.
Okay, fine.
So I'm not able to see how the links will move. Like one link can pull the manipulator towards its, one motor can pull the end effector towards itself, but how will the other two react to it? Means it's not clear.
I'm not getting your question. Oh, okay. All right. So I have this platform here, right? I have the platform here. So I'm essentially connecting let's look at just simply this plane. So I have a 2 jointed link. Okay, it's a diode. Suppose I want to move it here, right? So corresponding to this, 2 link would have reconfigured, isn't it? So that's possible to reconfigure this link. Similarly, it's possible to reconfigure the other link also.
So if I look at one particular motor, and if this is the end effector and these are the motor arms.
Yeah.
If I try to move it like this,
Yeah.
can it?
Yes, it can.
So then there has to be a
Oh,
rotating joint.
no. Okay, let's see. Oh, what you are missing out is, see, when you have essentially a parallelogram, is this on? No.
radius of the
No, this arm is different. See, this is a parallelogram. This is a parallelogram, right? So, since this is a parallelogram, when this moves,
that is on.
oh, this is on? Oh, wonderful. So, see, there are these joints here. So, what you are looking at, what you are not looking at is from this configuration, I can go to this configuration also. Okay. So, you have got to allow the transition to this configuration, and then if I look at this line, then there is also possible the rotation about this line. I think you are visualizing only the rotation about that line. So, this you have got to allow also. The interesting part is, even when this parallelogram reconfigures into this dotted line configuration, you still have this line being parallel. So, the parallelity is maintained, but you have that added degree of freedom in that direction. So, that is what is absolutely essential to allow this parallel motion to happen. Okay. Is that clear? So, this is another platform, again, which is known quite classically. By the way, the delta manipulator was kind of thought about in the 1920s and 30s, and then completely forgotten. And then, so in the 90s, another professor in EPFL rediscovered it, and then somebody pointed out that this has been known since 1920s. So then, but then now it's again even used for quite a few applications now. Okay, so even though you can think about a theoretical concept, by the time it becomes a useful thing in the industry, it takes a while. So this one is another interesting concept. So what happens is, yes, you have a linear actuator, right? But then there's the base. Now this line, this rotation axis which is there, so you don't have 2 degrees of freedom in all of them. So you don't have a spherical joint. You have a 2 degree of freedom axis here and a 2 degree of freedom axis here. Okay, there are no 3 degree of freedom axis. Now this line, and then the other axis is normal to this. You have this line, other axis is normal to this, and you have this line, other axis normal to this. So these lines, if you join them, they form an equilateral triangle. Same on the top. Now this is a special case, and what happens as a consequence of this is that this top platform, it can do a roll and a pitch, and it can heave in the z direction. Because of induced symmetry, it is able to translate in the z direction, but it cannot twist about the z, and it can roll about the other 2 directions, but it cannot translate in those 2 directions. So this is a special case. Okay. Like the delta is a special case, this is a special case also. So there are many such special cases which are there, and before you choose to actually design a manipulator afresh, you need to have a close look at the literature to decide what configuration you want to go to. But some of them are very standard. Like this one is a heave pitch roll is a very standard configuration which you can use. So now I'll get back to what we are typically good at in universities, which is writing equations, right? So now let's see. So we take a frame B, attach it to the base, we take a frame P, attach it to the platform. Okay. Now I can describe this frame in the base frame as the end effector position, no problem with that. So if I do that, now let's look at these 2 vectors. So this is the ith leg, one point is attached to the platform, one point is attached to the base. The length of the leg is Li. Now this vector from this origin to here, which I am calling RIP, okay, it is invariant in the platform frame. Similarly, this vector from here to the base of this leg is invariant in the base frame. Okay. Now, obviously, this RIP, I mean the vector from the origin of this to this is not, or the vector from here to here is not invariant, that changes as the platform reconfigures itself. Okay. Now, question is, we first work on the inverse kinematics problem. Okay. The issue is that if you are given the matrix P which describes the top platform, find the length of the leg. Okay. Inverse kinematic problem, we took the end effector position in serial manipulator and says find out all the joint angles. In this case, I want to find out the length of the legs for the generic hexapod. Okay. So, vector to a top of leg I in a platform frame is RIP, very simple. So, vector to top of leg I in the base frame is P times RIP. Just multiply by the transformation matrix, right, and I am in business. So, vector to the base of leg I in the base frame is RIB by definition. So, vector from base to top of the leg is P times RIP minus RIB. Okay. So, the length of the leg is very simply the norm of that vector. Okay. So, you have solved the inverse kinematics problem. Is this clear? Is it trivially simple? Or is it simple? Or is it not simple? Let us go back and review it graphically now. So, I know this, if I multiply this by the transformation matrix describing this coordinate frame, I will get this vector. I am saying the vector from here to here is this vector minus this vector. So, the length of the leg is norm of that vector. Okay. Only problem is there is a square root problem, but we can say the length is never negative, right. We want to keep the length positive. So, under the square root you can take the positive thing. Okay. So, that will resolve the problem. Okay. So, what is the next thing that we do? We do after inverse kinematics, we do forward kinematics or the direct kinematics problem. So, given the length of the legs, find the matrix P or equivalent description of the top platform. So, matrix P, or you say X, Y, Z, roll, pitch, yaw, whatever you want. Okay. Now, this is not a trivial problem. Okay. It is quite difficult. I mean, the other one I call trivial because after you have been through transformations and doing this little bit of matrix is not a difficult task. But this one is a quite difficult task, and the number of solutions to the general parallel manipulator problem, people have shown it to be 40. Okay. And and this was known fairly late, I mean roughly 1990s, early 1990s. So, till that time people are still struggling with it. How many solutions are there to this? Even 40 is, however, it is possible to derive analytical solutions for some cases, usually the special cases. I am talking about the general one where all the 6 legs are connected and all the 6 bases are not in the same plane, right. It does not, see 3 points define a plane. So, if I have 6 legs, they do not need to be in the same plane, right. So, platform below does not have to be a single plane, neither does thing on top have to be a single plane. You can connect them to any rigid body, making sure that no 3 of them lie in a single flat plane. Okay, so, there are these complications which are there, and usually you use an iterative scheme to do the direct kinematics. Okay. Now, for serial manipulators, do we know iterative scheme to do inverse kinematics? Use Jacobians. Okay. So, now we need to worry about the Jacobian of a parallel manipulator. Okay. So, what we want to do is we want to relate the articular state, that means the length of the legs and its derivatives, specifically its derivative, to the twist of the end effector, the way it is moving, the velocities. If I do that, then I essentially get the Jacobian. So, we write it in this form, capital theta dot is equal to J inverse W, where W is the twist. Now, I want to spend just a minute on something. The fundamental definition of a Jacobian is that it relates differentials in one coordinate system with differentials in another coordinate system. Now, why is it that I want to write J theta dot is equal to W? Okay. Or in the serial manipulator case, I again wrote it in that form. Okay. J theta dot is equal to Vx Vy in the planar case. Why is it that I don't write it the other way around? Right. If I write, in this case, if I write, I could have also written theta dot is equal to J times W. Okay, and we know that they are inverses of each other. Why is it that I write J like this? Because typically you write the J, that is the Jacobian used for inverse kinematics. Okay, so that is a typical Jacobian which is written down. So just keep this in mind, that if you just go by the strict mathematical definition, Jacobian can go either way, from one coordinate system to another one. But we in robotics we use this specific form, okay, which is this Jacobian, which multiplied by the actuator rates gives you the rates of the end effector, and not the other way around. Just keep this in mind. So if I happen to be using the other Jacobian, please catch hold of me. Okay, I should not, if I have done things right. Now we have already seen that the direct kinematics is difficult in this case. Okay. And if you cannot do the direct kinematics, then the Jacobian is very difficult. Right. How did we do it for the serial manipulator? The direct kinematics was very simple, so I knew all the joint axes, and I could simply put my screws in that direction, and I had a Jacobian. Right, it's quite simple. In this case, we know that direct kinematics is difficult, but there is this brilliant relationship, F is equal to J transpose tau. Okay. Now this is the same Jacobian, okay, as this Jacobian, except that you take the transpose. So in this originally we wrote the screws in this order. In this case we just transpose it. Okay. Where F is a wrench on the end effector and tau are the articular forces. So the joint torques in case of serial manipulators and the force moment combination applied at the end effector. I am not giving a proof for this now, we will do it later in the course, but you can pretty much understand where it will come from, right. Where will it come from? You have done planar dynamics, right? Do you remember the principle of virtual work? What does it say? F dot V. What is F dot V? That is energy done by at a point by acting forces, isn't it? If you apply a force F, what is the work done by it? Is F dot V at that point, right? So you sum up everything, that is the work done by the sum of the force at a point, and if an object is in equilibrium, then it has to be 0, right? This is F, this is essentially V. So, if f dot v happens to be equal to 0, you can show that, and now if any work is done, the work has to be done by the actuator itself, right. So, this times this summed over each actuator also has to be 0. So, if you do that, you can show that this has to be equal to J transpose. Okay, it's a very simple proof, I will not get into it, but this is a known relationship, and maybe when I do the dynamics portion we will derive it. So, the velocities and the applied forces moments are very closely related together, and you already know it through screw theory because they have to be reciprocal spaces. We do not formally study it in this course, but this is a extremely useful relationship. Now, why is this relationship very useful? So, this is what we do. Now, we know that any given system of wrenches acting in parallel on a body reduced to a single resultant wrench about a screw. Okay. So, we can write the line equation of each leg, no problems, because I know what this end effector position is, I can do inverse kinematics, so I can write the line equation of each leg, no problems. So, the wrench about each leg is tau I times the screw $I. If I sum it up, sum of wrenches, I will get the F acting on this body, right. Just flip back. So, I know F and I know that I get it in the form J transpose tau. So, you get J transpose, you get it by simply writing these screws $1, $2, $3, $1, $2, $3, $4, one after the other in this form. Okay. So, that gives you J transpose. So, if I know J transpose, I can find J and then I can do the direct kinematics. Okay. So, this is what makes, that is why you need screw theory. Okay. I mean the manipulation there is simply to use it for cases like this, that is to move between direct inverse kinematics, move between the force domain and the static equilibrium domain and the velocity domain. It gives you a very elegant formulation to handle them. The rest is exactly like you did the 3D serial manipulator. So, we will work more on that in through the labs as you go through. So, is this reasonably clear? Okay. I will give you some problems to work on. So, we will see. Now, so want to look at a more concrete example. So, I have just taken, you can look it up. So, people make hexapods all the time. Okay. So, you can see the rough size of this, you can see a monitor here, right, sticking around here. So, that gives you the rough size. It is about the size of a monitor. I mean, you can immediately know this is old because you do not see monitors like this anymore, right. Things of the days past. But I want to spend time discussing that. So, they have this HR2 motors, 6 of them, and then they have this encoders, okay, 6 of them, trying to measure what the motor is doing in this axis. Now, these gizmos are very interesting. I expect you, I mean, you should have, but this is all I will tell you about devices. So, you can go to this site, you can look it up. So, they make this high precision ceramic motors. Okay. So, they have unlimited stroke in the sense that they have these two things which move in and out of it. So, as long as you do not throw it out, you do not move anything. So, you could, but essentially it is a differential motion system. So, you change something, it just moves one of these white things with respect to the other one. So, you just connect this together, so this will move out, this will move in, and things like that will happen. So, it is a linear actuator, it is fairly compact, it is used for microscopy, precision motion, some micro robotics, small robotics application. And essentially for the operation, the electronics is very similar to a DC motor. Okay, so you can use DC motor controllers pretty much on this. The physics people call it amplifiers. And so these are high vacuum compatibility. What does it mean? Yeah, so why can't you use a regular motor inside a vacuum? Oils and lubricants, they will just get sucked out of that place and mess up your vacuum pump. So they have no oils and lubricants essentially in there. What is the other thing that will happen in vacuum?
So the air gaps inside will try to break out.
There are no air gaps, there is no air there, which means there is no convective heat transfer, right? So it's going to be hot. So you got to have something which either there is no energy wastage, but if you have coils or something, there will be I square R loss in there, so that has to be dissipated. So you got to take care of it. So you need to build up conductive paths and things like that out of it. So special problem. So there is a problem everywhere to be solved. Okay. Now this is equally interesting. So you have a linear encoder. Now what does it consist of? It consists of a tape and a reader. Okay. Now this tape has 20 micrometer graduations on it. Okay. Now this device, it allows interpolation of, so this 20 micrometer is a very basic resolution which you have on the tape. So you are marking the 20 micrometer. How much is that? 50th of a millimeter. Okay, so it has got really fine markings on it, and you get very long tape lengths. You can just cut it off and put it in. Okay. The Renishaw is a very famous company for metrology. Have you seen a Renishaw instrument? We have one here, right? TallySurf or something. And the CMM is also Renishaw. So they specialize in precision measurement. And you can interpolate, and you can go down to a resolution of 5 nanometers or lower. You understand interpolation? No. You have seen a vernier. What is the marking on the scale? Resolution? One millimeter, right? Typical vernier, right? But how much can you read using that? 0.01? Yeah, well now you have, actually is right. Now the other day I saw a funky vernier which had essentially it had this so you have the main scale, and then the sliding scale on it actually had 100 graduations on it. So you could go down to point, this is almost like a micrometer. Okay. Well definitely, but you definitely get something which have 20 markings on it is very standard now. So you can go down to at least instead of 0.1 millimeter, you can go down to 0.05 millimeter quite easily on that. A micrometer has again a basic graduation of about a millimeter and go down to 0.01. So how does this happen? So they use essentially equivalent thing, right? And then they have this counts on it. So they can go down to something like 4000 or something count below this. So 20 divided by 4000 is how much? Yeah, it's about 5 nanometers. So you can measure things with 5 nanometer accuracy using these kind of things. Okay. And it works out. So before I get down to geometry, so I come back here. So this is what the system is, and so what you can see is typically this is the encoder, or this is the encoder in the picture, and the little actuator is stuck in there, and the actuator moves this whole red thing up and down with respect to the purple colored thing. Okay, so it slides up and down in there. So this is the device, and you can see this can be fairly accurate. And what will you do using this? Typically optical placements or placing dyes when you do semiconductor thin film activity. So you can control the resolution fairly accurately using this. Okay. So, what we will do is we will stop here, and on Friday, from whatever time we have left after the exam papers thing, we will try and use this and actually do some concrete examples of doing the forward and inverse kinematics of this device. Okay. So, any questions? It's a very good class, very few questions, understand everything, and so consequently we are going at a phenomenal pace.